Continuing with our definition of interpretation as defined in the previous video, now we'll look at how to actually determine the interpretation of a particular well-formed formula. So given a particular interpretation script D, given by the pair D, the domain, and M, the mapping we defined previously, we define the translation of A, or we determine the translation of A following some particular rules. So, in particular, the interpretation A with respect to the interpretation script D is obtained by following the following rules. So 1, if A contains a universal quantifier, we replace that universal quantifier with the universal quantifier applied to the particular domain here. So instead of for all x in general, when we have that for general well-formed formulae, instead the interpretation is specific to for every x in the domain, right? Because the object variables all belong to that domain in this particular interpretation. In addition, since we are generalizing over this particular variable x in D, right? If it's a variable bound by a universal quantifier or even an existential quantifier, we keep these bound object variables unchanged. So for any x that occurs in A where the universal quantifier appears, that x remains because we are making a statement about a general x, so about all objects in the domain D within that statement. And then finally, we apply our translator M to every other substring of A. Right, so that translates any Boolean variables and Boolean constants to the corresponding true or false, depending on how we specifically define M, and it translates any free object variables or any object constants into members of D that we define by the specific translator M, and it translates or defines functions with respect to the translator M and predicates with respect to the translator M, and everything else remains unchanged. So, considering all of these rules, now let's see some examples. So, let's consider the well-formed formula x equal to y. Then, to apply this interpretation, so A superscript D is A applied to a particular interpretation. So in general, we will, following these rules, since there are no quantifiers, we will translate everything here. So whatever M applies, so we apply M, so we get x translated by this interpretation, and we translate y with that interpretation, and recall everything else remains unchanged, so in particular the equal sign remains unchanged. So now, for a particular interpretation, let's define our domain for this particular interpretation to be the set of numbers 1, 2, 3. So the first 3 natural numbers is our domain, and then we define M. So that means we have to define our translator, which translates all object variables, constants, and everything else. But notice that we only need to translate what actually occurs in A. So we only, in this case, need to specify what xd and yd become with this translator M. So let's recall that the object variables have to be members of our domain. So once we've defined our domain, this helps us to determine what xd and yd will become. So we define M so that xd is 2, a member of the domain, and yd is 3, which is also a member of the domain. Then, in particular, applying this specific interpretation that we have defined here, our interpretation of A with respect to this specific interpretation is the statement 2 is equal to 3, which we know is false because 2 is not equal to 3. Okay, so that's one example of how we apply an interpretation to a particular well-formed formula and then evaluate the truth value based on the knowledge we know with respect to that particular interpretation. Okay, let's look at another example which is a bit more complicated. So now let's add in this universal quantifier to give you an example of how to follow these two rules in the translation of A. So if A is for all x, x equal to y, and notice that this is in the scope of this quantifier here, then our original general interpretation of AD would be, first of all, for all x and d, right, applying this first rule here to our universal quantifier, and then recall that we keep any bound object variables unchanged. So since x is bound by this quantifier, it remains unchanged, but we do interpret y. So if we use the same interpretation here, then we know yd becomes 3, and so this is our interpretation of A with respect to this particular interpretation. And again, notice that now the statement is for every x in the set 1, 2, 3, we claim x is equal to 3. That's what the statement is. But we know this is false because, for example, 1 is a member of the domain and is not equal to 3. Or, as we discovered in our previous one, 2 is a member of the domain which isn't equal to 3. So, again, we have that this statement is false. If, however, we changed our domain D to be just the set containing 3, then this would become true. So depending on the interpretation, can change the value from true to false. As you can imagine, as we go further in, when we're looking at counter models, we simply have to find a model which is going to make this false to specify what the semantic meaning of the well-formed formula is. All right, let's do one more example. So now suppose A is the first order formula for all x phi xy, where phi is any predicate. Again, considering this specific interpretation, what we need to interpret is not only x and y, but now because we've added an additional member of our alphabet to A that needs to be interpreted, we have to give that interpretation. So we defined phi d to be some relation which acts on D. In particular, let's let it be the relation less than or equal to. So then the interpretation of this becomes for every x and d, again applying this first rule here, x less than or equal to 3. So right, this would be x less than or equal to y. Again, x is bound, so it stays the same, but y gets translated to 3 by how we've defined m. So now we have AD is the statement for every x in the set 1, 2, 3, x is less than or equal to 3. And this is in fact true, right? Because 1, 2, and 3 are all less than or equal to 3. To conclude section 8.1, we want to define also what a partial translation of a formula is. So a partial translation of a formula A by an interpretation D with respect to the variables x1, x2, xn is first denoted by A with the subscript of these variables and a superscript D. So here, a partial translation essentially relies on some object variables, and the partial translation is simply translating everything in A while leaving x1 to xn untranslated. So if, for example, we wanted to leave some of our object variables not translated, then we talk about a partial translation instead of a complete translation. So, for example, what does this really mean? So if A is the well-formed formula x1 equal to y or x2 less than y, then the partial translation of A with respect to x1 and x2 under this interpretation D becomes the well-formed formula where we leave x1 and x2 as object variables but translate anything else. So in this case, we only translate the y's. This doesn't have a lot of applications really, except that this allows us to give a shortcut for what we mean by the rules in translating any formula. So for example, recall we had particular rules that applied when we translated a formula which involves a universal quantifier. And we know, first of all, that within the universal quantifier, we insert the domain of the translation we're talking about, or the interpretation we're talking about, but then recall that we leave the variable associated with the quantifier unchanged in A. So this is how we can denote all of those rules that we defined in the translation before, right? So inserting the D and leaving all of the X's and not translating them with respect to D in A. Okay, so this concludes what we will cover involving translations and partial translations of well-formed formula and interpretations. Next, we'll look at an introduction to how to apply this to construct countermodels.